Let us now discuss about Van 't Hoff's equation. Just like the Boyle's law, what we discussed, here we can give Van 't Hoff Boyle's law. It can be given as osmotic pressure is inversely proportional to the volume of the solution at constant temperature. And as we know that volume and concentration are inversely proportional, the same can be given as pi is proportional to C at constant temperature. Okay. Concentration and volume are inversely proportional to each other, like molarity, normality, whatever. But here in this case, of course, we consider molarity. Now, take Van 't Hoff Charles law. Pi is proportional to T at constant volume. Now, from these two, it can be given as pi is proportional to T by V, right? Or in this case, it is pi is proportional to Ct. Now, pi V is proportional to T. Pi V is equal to St, where S is a constant. It takes up the value 0.0828 liter atmosphere per mole per Kelvin. Almost the same as the value of gas constant R, which of course takes this value, right? So this S can of course be modified as R, and see this is for 1 mole. When we take for n moles, it can be given as pi V is equal to nRT, right? On to the other hand, this can be modified as pi is equal to CRT in terms of concentration. So these are the two very important relations. Pi V is equal to nRT, pi is equal to CR. Okay. Now this pi V is equal to nRT can be modified as pi V is equal to W by M dash into R, right? Where M dash refers to the molecular weight of solute. As usual, even here also, the magnitude of osmotic pressure is inversely proportional to the molecular weight of solute. Okay. Now let us see three very important points. The first one is isotonic solution or isosmotic solution. Now these are the solutions having same osmotic pressure. Pi 1 is equal to pi 2. See, when they have same osmotic pressure, they of course will have the same molar concentration. I mean same molarity. So therefore it can be given as a C1 is equal to C2. So the solutions having the same molar concentration are said to be isotonic solution. Then the second one, hypertonic. Hyper is more, hypo is less. Hypertonic, a solution, it's a relative thing. A solution having higher osmotic pressure than the other is said to be hypertonic. Okay. In this case, pi 1 is greater than pi 2 or C1 is greater than C2. This is hypertonic. The other one which has got lesser osmotic pressure, of course, is said to be hypotonic. Hypo, less. A solution having lesser osmotic pressure than the other is hypotonic. Okay. Pi 1 is less than pi 2. C1 is less than C2. Now this is hypotonic. Okay, so these are the three very important points in this. See, osmotic pressure has got some advantage. The advantages are, in this, molarity is used rather than molality, what we use in case of the other colligative properties. Okay. In some other way, of course, it is a disadvantage also. Because molarity depends on temperature, whereas molality is independent of temperature. But as far as calculation is concerned, molarity is good because we go with volumes rather than weight, which we use in molality. It's better, it's advantageous to go with the volumes of the solutions rather than the weights of the solution. That way it is an advantage, right? Next. And here the osmotic pressure is calculated at room temperature rather than the drastic conditions like very high, what we use in elevation in boiling point, or very low, what we use in depression in freezing point. Room temperature is used in osmotic pressure calculation. The last very important point is the magnitude of the colligative property. See, magnitude of the colligative property in case of the osmotic pressure will be a significant value, a considerable value, obtained even with very dilute solution. Unlike the elevation in boiling point or the depression in freezing point, where we get values like the delta TB generally will be in points like 0.00 something or 0.000 something. Same is the case with depression in freezing point also, where we get very low values, like again in decimals. But here, it will be a significant value. It will be a considerable value. So in this case, magnitude of pi is very high or is high even with very dilute solution. This is the reason why we generally use pi for the calculation of molecular weights of macromolecules. Macro means big. Macromolecules like the polymers, protein. Okay. Let us now discuss abnormal molar masses. First of all, what are abnormal molar masses? Let me give you three examples. Example 1, glucose. Example 2, sodium chloride. Example 3, acetic acid. Okay. Now, let us suppose 100 molecules of glucose are dissolved in water. The solution, whatever is formed, will have 100 molecules only. Not only glucose, even urea, sucrose kind of things. It is because, glucose neither associates nor dissociates. That is the reason why we can see the same number of molecules even after dissolving in water. No change. Next. Coming to sodium chloride. Let us again take the same 100 formula units of sodium chloride. When dissolved in water, the aqueous solution will actually have 200 particles. If suppose it undergoes dissociation to an extent of 100%. 100 molecules, if dissociate to an extent of 100%, will give us 200 particles. We can see 200 particles in the solution. It is actually because of the dissociation. Now let us take the third example. Let us again consider the same number of molecules of acetic acid. When dissolved in benzene, here the solution consists of only 50 particles. If suppose this undergoes 100% association. So there are three different issues. No association, no dissociation. The number of, let us say, particles remains the same. If there is a dissociation to an extent of 100%, let us say, maybe 100%, or it may be something else, but for now, let us consider it as 100% dissociation, which will result in the double the number of particles. If 100% association is considered, the number of particles is halved. We know two very important things. The first one, see the magnitude of any colligative property is directly proportional to the concentration of solute particles. Now, let us consider this. If you consider the magnitude of colligative property in the first case, there won't be any change or it remains the same, because the number of particles has remained the same. Whereas in the second case, because the number of particles is doubled, even the magnitude of colligative property is also doubled. See the changes. In the third case, the magnitude of colligative property is halved because the number of particles is also halved. Right. Now, what happens if the number of particles changes? We also know that the magnitude of colligative property is inversely proportional to the molecular weight of solute. Now, when the magnitude of colligative property changes, then the molecular weight of the solute also changes. In the first case, of course, it remains the same because there is no change in the number of particles, no change in the magnitude of colligative property. See, in this case, because the magnitude of colligative property is doubled, the molecular weight is halved because magnitude and molecular weight are inversely related. In the third case, because the magnitude of colligative property is halved, the molecular weight of solute is exactly doubled. If you consider this, it remains the same as 180. In this case, when calculated from one of the colligative properties, rather than getting 58.5, we'll be getting 29.25, right? And in the third case, rather than getting 60 from one of the colligative properties, if at all it is calculated, we'll be getting it as 120. So that is all about the abnormal molar masses. You can see these two. Molar masses either higher or lower than the normal or abnormal molar masses. Okay. Now, to actually account for these abnormal molar masses, Van 't Hoff introduced a factor called Van 't Hoff factor. Van 't Hoff factor represented by I. Say this I can be given in three ways. Number of particles in terms of number of particles as number of particles after association or dissociation by the number of particles before association or dissociation. Simply it is after by before. Okay. Like for example, if you observe in case of sodium chloride, after it was 200, before it was 100. So the value of I is 2, anyway greater than 1. If you observe the same in case of acetic acid, after it was 50, before it was 100. So in this case, the value of I is half, less than 1. In case of glucose, if you observe, it is the same. after as well as before. 100 by 100, it is equal to 1. So we can give three different values: equal to 1, greater than 1, less than 1. We'll give them, of course, but let me give you two more relations. See, after association or dissociation can be given in terms of the magnitude of colligative property. Observed. Observed means after conducting experiment by the magnitude of colligative property actual. Yes. Now, so after is nothing but observed. Observed is nothing but experimental. Let us go with observed magnitude by actual. Actual is the normal one. Experimental or the normal one. Now, see, the magnitude of colligative property and the number of particles, these two are directly proportional. So we got them as after by before. Similarly, experimental by observed. But when we go for the molar mass or the molecular weight, it will be okay. The molecular weight of solute normal or actual, because this is inversely proportional. The normal has come into the numerator. The molecular weight of solute observed. M normal by M observed. So the first two are directly related, whereas the last one is inversely proportional. Normal by observed. Now, like I said earlier, we can take three cases. The first one, as in case of glucose, if I is equal to 1, we can say that there is no association, no dissociation. And if I is greater than 1, it refers to dissociation. Then, if I is less than 1, it refers to association. Okay. See, I is equal to 1 is of course normal. Either greater than 1 or less than 1. We say them the abnormal. Abnormal molar masses are in fact due to this dissociation and association. Let us now rewrite the expressions for all the colligative properties that we have discussed so far, making use of I mean the band half factor. Otherwise, They can be used only in case where you don't have any association or dissociation. Let me give you. We know that RLVP is equal to mole fraction of the solute. It's a common one where you don't have any association or dissociation. But if you want to use the same even when there is association or dissociation, include I, right? This is the first one. Now let us go for the second one. Delta TB, I mean the elevation in boiling point. We have given it as Kb into small m till now. Let us now include I. Now it can be used for any sort of solute. Then the depression in freezing point, delta TF. Earlier it was Kf into small m. Now modified as I into Kf into small m. Final thing is pi, is osmotic pressure, normally given as a CRT, but can be modified as I into CR. So in all the expressions for colligative properties, now we have included Van 't Hoff factor I. So these modified forms can be used for calculating the magnitudes of these colligative properties in case of different types of solutes, even if they undergo association or dissociation. Okay.